Hello, in this talk, I will present our results on the problem of coloring the nodes of a graph with delta colors in the distributed setting, where delta is the maximum degree of the graph. This is joint work with Sebastian Brandt and Alexandre Nolin. The distributed model which we will focus on in this talk is the distributed local model. In this model, a network is represented as a graph. The nodes are computational entities, and the edges are links that the node use to transmit messages between each of them. In this model, the graph is denoted as G. It is undirected. N is the number of nodes in the graph, and delta is the maximum degree of the nodes of the graph. The model works in the synchronous way. During one round, nodes first send messages of unlimited size to each of the neighbors. Then, the nodes receive the messages from the neighbors. After that, nodes can perform unbounded computation. The complexity is measured in rounds. The complexity of an algorithm is measured as the number of rounds until the last node terminates. In this model, every node is given a unique ID. Let's get first some feeling about what is happening during the execution of an algorithm in the local model. Initially, a node has no knowledge about his neighbors. As here in the picture, node or in a range, only knows its own ID and itself. Then, after a round, the node has received messages from each of its neighbors. In that case, he knows his entire distance 1 neighborhood. After one more round, the node will know its entire 2-hop neighborhood. This happens because since nodes can send messages of arbitrary size to each of the neighbors, a node can simply send to each of its neighbors at least everything it has seen so far. So after 2 rounds, a node knows its entire distance t neighborhood. It has been shown that a large part of the problems studied in the local model fall in the category of locally checkable problems. These are problems that can be defined by local constraints. Among those problems, one can cite delta plus 1 coloring, maximal matching, maximal independent set, the local lover's lemma delta coloring, or 2 delta minus 2 edge coloring. An important result from 2016 has shown that every of these problems belong in one of the 2 following categories. Either the problem has an algorithm in f of delta log star n, or the problem has a lower bound of log n, which stands even for constant delta. Taking delta as a constant is actually a very natural thing to do in this model. And notice that there is a big gap between some problems that can be solved in log star of n and some problems which have a lower bound of log n. For the problems of the first category, an algorithm of log star n has been found for all of the most important problems, which contains the ones that have been cited so far. But for the other category, only very few problems have a log n upper bound. To my knowledge, actually only one, synclass orientations, and some other problems that derive from it. For this reason, it's interesting to see if one can close bounds for other problems of this omega log n complexity class. And one of the most important problems in this category is delta coloring. First, delta coloring was a problem used to show that there is an exponential separation between deterministic and randomized complexity for some problem among locally checkable problems, and show that this separation cannot be bigger than exponential. This comes from work of Cheng, Kopelovitz, and Petty, and also work of Brandt, Fisher, Hevonen, Keller, Lempian, Rebecca, Suomala, and Witte. While obtaining this exponential separation, a new technique to obtain lower bounds was designed, round elimination. This technique has since been crucial to obtaining new lower bounds in the distributed model. Also, delta coloring and the reduction of it has been used to obtain several lower bounds for very different problems, such as maximal independent set on trees, which comes from work of Baliu, Brandt, Kuhn, and Olivetti. Let's have a look at the state of the art. As mentioned previously, the lower bound in deterministic is of log n, and in randomized of log n. For the upper bounds, there are several things. For any log n, we have this log square delta log n plus log square n upper bound, which comes from combining work of Gaffari and Grunow and Gaffari-Kuhn. But when delta is constant, the best upper bound is still log square n, which comes from Panconesi and Srinivasan in 1995. So there has been very little progress so far, as this is the initial paper which considered delta coloring in the distributed setting. In randomized, there has been also lots of progress. Is now polylog-log-n algorithms for delta coloring, coming from work of Gaffari, Hevonen, Kuhn, and Maus, and Fisher, Maus, and Halldorson. But when delta is constant, there is still a log square log n upper bound. Our results get an almost tight complexity when delta is constant. In particular, we get in deterministic a log n log star n upper bound, which is almost optimal up to this log star n factor, and in a randomized, similarly, a log n times log star n upper bound. The most important problem we need to consider when we talk about delta coloring is Brooks' theorem, which states that every connected graph is delta colorable except clicks and odd cycles. In our case, we will consider only connected graphs which are delta colorable and for which the degree is greater than 3. But now let's figure out how to color with delta colors. The first thing that one can notice is that nodes of degree less than delta minus 1 can always be delta colored no matter the coloring of the neighbor, because they can always pick one color between 1 and delta. So a connected graph which has a node of degree less than delta minus 1 is delta colorable. And we can use this node of degree less than delta minus 1 to color this graph. A way to use this node is to build layers. Let's look at the picture. First, we start with a layer where we put every node which has degree less than delta minus 1. And then we'll build new layers, adding in every layer all the nodes which are distance 1 of a layer. Once this is done, we start by coloring the nodes in the upper layer. This node can always be delta colored because it has a neighboring node in the lower below, which is uncolored and which will not try to be colored at the same time. We apply this algorithm, this coloring algorithm, for every layer, and then the whole graph will be delta colored. However, not every graph contains nodes of degree less than delta minus 1. Thankfully, we can use the following lemma, which shows that at distance less than 2 log base delta of n of a node, there exists either a node of degree less than delta, or a subgraph of diameter less than 2 log base delta of n, which is delta colorable. This subgraph is just any subgraph which is two connected, not an circle and not a clique. A technique to color any graph is then the following. We first build a ruling set, which is some extension of MIS with higher distances. Here, the blue nodes are the nodes of the ruling set. They are at distance at least log n of every other node of a ruling set. Every node which is not part of the ruling set, here the node in orange, is a distance at most log n base delta times polylog log n. Which means that one can do as previously. First, we build a layer, starting from the nodes outside the ruling set, and recoloring towards the nodes of the ruling set. Once this is done, since the distance between two nodes of the ruling set is at least 4 log n, every node of the ruling set can identify a subgraph or a node of color of degree less than delta in its 2 log n neighborhood, and then can use them to color their neighborhood with delta colors. The problem of using this technique is that it has inherently a log square n complexity in terms of rounds, which we want to break through. So we designed a new technique which doesn't need this kind of ruling sets, even though we will use ruling sets in this technique. For this, we show the existence of a variation of the delta colorable subgraphs, which are called locally delta colorable subgraphs. Look at the picture. The vague idea is that on these subgraphs, we can build an area of constant diameter. And in this area, we make sure that two nodes can get the same color and be neighbors of one node of the subgraph. From then, one can make a path containing all the nodes of the subgraphs towards the root node, which is a node with two neighboring nodes of the same color. But there is still a need to break symmetry between the subgraphs. If we look at the picture here, one subgraph makes a path going through the area of the other subgraph. If both subgraphs are trying to recolor each at the same time, then the first subgraph would modify the colors in this area of the second subgraph, and then a delta coloring could not be achieved. Hence, we need to break symmetry between the subgraphs. To achieve this, we design an algorithm to build subgraphs, ruling sets on subgraphs. Recall that ruling sets are some extension of MIS. As input, we take a family S of subgraphs. And as output, we output a subset W of S, which will be a ruling set, such that every subgraph in W has no neighbor in W. So here, neighboring subgraphs are subgraphs which intersect the area of the other subgraphs. And every subgraph which is not in W is at short distance in G to a subgraph in W. Just applying MIS would be inefficient because the subgraphs can have high diameter of log base delta of n, which would give us a very bad complexity. So here is our method. So we consider the virtual graph composed of the subgraph where we add an edge between two nodes when the subgraphs intersect the area of the other subgraph. Because the subgraphs are made of log base delta of n nodes, the degree in this virtual graph can be of factor of n. Here I will show how to reduce this degree to log base delta of n squared. Every subgraph creates a token, which is a node in black, and we remove the token on every node of the subgraph, like so. After O of log n rounds, because subgraphs have log n nodes, the work is finished. One rule happens during this work. If several tokens are on the same node in the same round, every token is removed but one. And this happens the following way. The token just move on the nodes of the subgraph. Then tokens go back to the initial node. Some tokens have been removed. But now we have that the maximal degree in the virtual graph is at most log square base of n base delta. And then we can repeat this log star n times. Every time we'll gain a log n until the maximal degree in the virtual graph is of 1. And then we can do as before, recolor everything outside the subgraphs, and then recolor the subgraph in the last step, as we had shown. Our results are the following. We give how to show a subgraph ruling set in O of log delta plus log base delta of n log star n rounds. Algorithm can give a data coloring in a log square delta log n log star n rounds. This is almost optimal for constant degree, both indeterministic and in randomized. Thank you.